Okay, good. Then let's get started. We are recording now, and it's on Discord. So let's see. Today we'll start with a simple programming problem or two, just to make sure that you get some experience with the kind of programming that we need to be able to do for this course. As I mentioned previously, all my examples are going to be in Python, which is a very popular programming language. But you can also choose another programming language if you think that would be worthwhile. It'll just be harder than to, you have to do more work on your own. So the problem that we're going to look at today was actually posed as the BBC puzzle for today, which was the BBC radio show, and they would post various puzzles. So let's go and have a look at it. So unfortunately, they don't seem to be doing any new ones anymore. And also, let me just post. Right. Okay, 613. So the puzzle is, you have a stick that's 1 meter long, and you have tracks on a running track that are exactly 1 meter wide. And now you take your stick and you throw it in the air and let it drop down on the ground. Then what's the probability that your stick will hit or cross one of the lines? Now, you can actually solve that using geometrical probability. And the first guy to do that was actually Comte de Buffon in the 19th century or late 18th century. But since we are computer programmers and software developers and roboticists, we'll try and use a computer to figure out what that probability actually is. And then hopefully most of you will be surprised by the actual result. So any guesses beforehand?
problem that we can implement there. Have an AI system switch the cameras.
So I have tracks, 1 meter apart, then I throw sticks. So my first stick falls like that, doesn't cross any of the lines, right? So that would be 0 here, we cross the line, here we cross the line, here. We also cross the line exactly 1,000,000 times, like we just happened to hit it line exactly. Here we have one that's parallel, that doesn't cross any of the lines. Then if you throw this 100 times, what would you expect? How often do you think you would actually hit a line?
You would actually hit a line.
Like 10%, 20%,
10%, 20%,
50%.
50%.
Let me think. I don't actually know what the answer is.
I don't actually know what the answer is.
I think it's 66%.
66%, maybe.
We'll see later on. Okay, so that's also not something we can solve easily analytically. So even though we may want to use probability theory later on to verify our simulation, it's not a bad idea to actually implement this and then see what the result is, just to make sure that we have a proper understanding of the problem, and it also gives us some ideas for how to approach the problem. So now you can, hopefully you bought your laptop with Python installed, or you can use the lab computers, set them up, and then start implementing a solution for this to calculate this probability. And we want to do a little bit more because when it comes to AI, lots of times we need to run these kind of simulations. So we also want to be able to show the results. So you should generate a chart that kind of shows the probability as you throw more and more sticks. Because here they say throw it 100 times, but clearly the more often you throw it, if you have a real random number generated or a pseudo-random number generated that is accurate enough, then the more times you throw it, the closer you should approach the correct answer. If you only throw 3 sticks, very unlikely that you're going to get the right probability. If you throw 1,000,000 sticks, then much more likely. So we want to show some kind of chart to see how much that probability changes as we throw more and more sticks. So here's the task for today. Implement a solution for hockey sticks. 1 meter long happens to be about the same as the width of the lanes on an athletic track. If I toss the stick 100 times, then how many times do I expect it to land crossing one of the lines? And it was actually first posed in 1777. Posed and solved in 1777. So here's what it looks like. Tracks throw the sticks,
tracks,
and we have
and
to
we throw the sticks, and then we have to
simulate this environment.
simulate this environment.
And with any kind of computer program, the most important thing to worry about initially is how do you model this?
How do you model this on the computer?
Right?
Right?
So without writing any code yet, then how would you structure your program? What do you think you need?
Structure your program. What do you think you need?
Functions, okay. What kind of functions?
Functions, okay. What kind of functions?
Yeah, we need to generate some random numbers.
We need to generate
right?
some
Because
random
we're going
numbers.
to throw sticks randomly.
Randomly.
Generating random numbers on a computer turns out to be surprisingly difficult, actually, to do it correctly. There's lots of approaches that come to mind that you think should work well, but have hidden dangers, especially if you use it for highly sensitive data or very important encryption of data or modeling of data. So, because the computer really cannot, until very recently, computers really could not do proper random number generation. It was impossible to do anything random on a computer because you would follow the program, right? And you would have one program. Now, the latest generations of CPUs have proper random number instructions built in, RDRAND on the Intel CPU family, and the ARM has something similar. So desktop CPUs nowadays, they can actually generate true random bit, but it's a little bit slow. So people sometimes often like to use the true random number bit only as a seed into a random number generator, into a pseudo-random number generator. It depends on what you're trying to do. If you need to encrypt 100-byte message, then that's not a problem. If you need to encrypt large amounts of data, then that would be gigabytes and gigabytes of it, like banking kind of communication, then that would be too slow. So that's then when you use sort of a two-fold approach, where you take the true random bits to generate a seed for the random number, for the pseudo-random number generator, and the pseudo-random number generator generates billions of pseudo-random numbers. So that kind of thing works. Or in the encryption, you would use true random numbers to encrypt the public key. They're the private key, and the public key public anyway, and then you would use the encryption of that key to decrypt the key to encrypt this message. That kind of thing. Now, in Python, how do we generate numbers? Random numbers? Sorry.
Random numbers? Sorry.
It has the library built in, so we can use random, and you should not even think about trying to do this yourself. Like I said, if that is, I mean, for this particular assignment, it wouldn't matter, but if it for the outcome of the simulation, even it's most likely going to be highly similar. So you want to use the built-in random library. What other functions do you need? What does our program actually have to do? Yeah, so count the times that the stick hits the line, right? But before we can do that, we actually need to throw a stick, right? So somehow we need to model how we are throwing these sticks. And that will be a core part of the program. And then we also need to graphically display the results, which in Python we can use the excellent matplotlib library and NumPy in order to be able to do that. So plotting it is also not too difficult. There's powerful libraries for doing that. I actually personally, that is one approach that you can think about the problem, and for certain problems that works quite well. I find myself more, as I went through my career as a professor and programmer and developer and roboticist, I find myself that the functions, if you worry about the control flow, but worry about the functions first, then sometimes you can paint yourself into a corner. I actually think it is better to think about the data structures that you want to use first and come up with a good data structure to represent the problem. Because once you have your data structures, the code, the control flow is much easier to implement. If you start thinking about the control flow, then often you end up with very complex data structures which are difficult to maintain, and it becomes more difficult to actually implement. So now thinking about the data structures, what data structures would you want to use? Which means what facts do you need to represent in your program? Well, for every experiment that we do, right? What we need to determine is how many, if we throw n sticks, how many of those hit a line here. Right? Okay. In order to be able to determine that, what do I need to know? The position and the angle for each one of those sticks, right? So I have a collection of sticks. How would I represent those? In an array? Yep. That makes the most sense. Why? What would be other options? What else could we use to represent it? If I don't want to use an array, I could use many kinds of data structures, of course, but in this case we could be thinking about a list, right? And dictionary. Now the main difference, dictionaries allow you fast access to particular items if you want to store a whole bunch of them. That doesn't seem to be necessary in this case. I don't need to identify which stick hit this line, for example, or list all the sticks that hit this particular line. That's not necessary to answer the question, how many hits do I have on any of the lines. Right? So dictionary doesn't make any sense here. List would be okay. In Python they're okay because Python doesn't actually have, standard Python doesn't have any arrays. Right? And the difference between lists and arrays would be, for arrays you need to know if you think about C, C++ kind of arrays, Zig arrays, then you must know the size of your array beforehand. Right? At compile time you need to know how big that array is going to be, or at least when you call your function you need to know how big that array has to be. In this case, we would know that. We have, we'll pass in n, 100. Right? So I need to keep track of 100 sticks. So that means the size of the array is not going to change. Lists would be if you don't know if it's 10 items or a million items. 10 items or a million items that you need to store. Then a list would be better because it allows you to dynamically change the size. So okay, we're going with arrays. Now Python doesn't actually have arrays. In the typical sense, like C and C++, Python only has lists. But what the Python list is not the typical list that you're taught in the data structures course. It's actually an array list. It's a list of arrays. So it also is able to allocate extra items very efficiently and also go through this iteration through the list very quickly. So the Python lists are sort of a hybrid between arrays. If you do have to process a huge amount of data, like a billion examples for your machine learning training assignment, then how do you get true arrays in Python? That would be using NumPy package. NumPy is a very powerful package where you do get proper fixed size arrays that can be iterated through faster than the Python. If you use any kind of NumPy operation, it is actually calling C++ code underneath, so this runs very efficiently. The other difference between Python list and NumPy arrays is that in a Python list, you can pass in any arbitrary data. Like you can have integer, float, string, float, another list, all as part of one list, right? Whereas in an array, NumPy array is it's a 32-bit floating point, then every element has to be a 32-bit floating point. And if it's an integer, every element must be an integer. So the data type in a NumPy array. Okay? So for this particular problem, we don't really need much, except we need to have an array to figure out, like you said, the position and the orientation of the stick. Now, how do we model the entire thing, though? Like it's a little bit unclear. Right? In the problem itself, if you wanted to draw this,
if you
right?
want
You
to
really
draw
couldn't
it,
because
right?
you don't know how many tracks there
You
are,
don't know how many tracks there are,
right?
right?
Like how many tracks are on the running track? 8.
How
There's
many
usually
tracks
8
are on the running
tracks
track?
on a running
There's
track, I
usually
think.
8
But
tracks on a running track, I think.
it's not stated in the problem, so
It's
maybe
not
more,
stated
maybe
in the
less.
problem, so maybe more, maybe less.
But looking at this particular
But
problem,
looking at this particular problem, actually,
what about the position
what
of
about
the
the
stick?
position of the stick?
It doesn't matter. I mean, it does matter.
I mean, it doesn't
This
matter.
would be different.
This would be different.
This stick here and
This stick here and
this stick here, the position matters,
this
right?
stick
Because
here,
one
the
crosses the
position
line, the other one doesn't.
one crosses the line.
What does not matter is
What does not matter is
painted in orange.
painted in orange.
The y-axis does not matter. That's
The
correct.
y-axis does not matter. That's correct.
And also,
Huh?
the angle of the stick matters.
The angle of the stick
Because if
matters.
this stick is at this position,
If
it'll
this
cross the
stick is
line.
at this
If it's
position,
at this
it'll cross
position,
the line.
if
If
it
it's
has
at
this
this
angle,
position, if it has
right,
this angle,
then it will not cross the line. So that's a
then
big
it will not
difference
cross
as
the
far
line.
as
So
our
that's a
program.
big difference as far as our program is concerned.
But it's sort of
It's
modulo the
modulo
track, right?
the
Like this stick,
track.
this stick
Like
here,
this stick
and
here,
this stick here doesn't really matter.
and this
Doesn't
stick
matter
here
whether it
doesn't
lands
matter.
at that
Doesn't matter
position
whether it lands
on
at
track
that
1, track
position
2, track 3.
On track 1, track 2, track 3.
So we can now think about our representation for the position, and then okay, we need to model the position of the stick. If it's the position of the stick, then of course it seems intuitive to pick the center of the stick as the
The
position,
center of the stick as the
Right?
position. Right?
but I could also use this point or this
Also
point
use
here,
This point or this point here again.
like the leftmost one or the
Like
rightmost.
the leftmost one or the rightmost one.
And now, if we're only concerned about
we're only concerned
one-
about one
track, Then-
track.
let's say we only focus on one
Let's say we
line
focus
here,
on one line here.
and then we let the position of the center of the
Position
stick,
of the center of the stick.
we'll take that to be the number to the
Take
closest
that,
line that we
number
have.
to the closest line that we have.
That simplifies things too, I
That
think.
simplifies
So
things too. I
that
think.
means
So
if this is 1
that
meter,
means if this is 1 meter,
then I let the position of the stick range from minus 0.5 meters, which means the stick is to the left of the line, to plus 0.5 meters, which means the
plus
stick is to the right of the line.
meters, which means the stick is to the right of the line.
Okay.
Okay.
And then we need to know the angle.
Then we need
Now,
to
how
know
about the angle?
Now, how about the angle?
Depends on what you mean by better. There's really no better. We just count hit or
There's really
miss.
no better. We just count hit or miss, right?
So we don't really have any better.
So we don't really have any better, but
You're sort of in the right track.
you
If
sort
I
of
take
are
this
in the right
as
track. If I take this as
P1 and this is P2,
P1, and this
or that stick is rotated by 180
is rotated by 180
P1,
degrees, P2,
then that doesn't really matter.
then
Right? So the angle that we want to
model
is from
is
only 180 degrees.
only 180 degrees, I guess.
From here to there.
From here to there.
We don't consider the inverse angle.
We don't
because as far as hitting the line is concerned, that's exactly
hitting the line is concerned, that's exactly the same.
There's the stick, the center is here, and
the center is here,
the stick is this many degrees, then that's the same
degrees, then that's the same as the
orientation.
at this
And center that
orientation.
between the
And
same,
center
the two ends are either
the two ends
are going to hit the line or
are
not.
going to hit the line or not. It's going to be the same. Okay.
So that's the first observation. Actually, we could simplify that further and simply make it 0 to 90 degrees.
Make it 0 to 90 degrees when you think about it. Because
we have this bit, and we have this bit, to 1,
this is 2, 1,
this is 1, 2,
this
right?
is 1, 2, right?
So those are actually overlapping.
So
They're
those
just
are
rotated
actually
by
overlapping.
180
They're
degrees.
just rotated by
But
180 degrees.
this stick here
This stick here,
that is 90 degrees off.
that is 90 degrees off.
So
So 2, 1.
if this stick is going to hit the line, this one is going to hit the line as well, just below rather than above
rather than above the
But we don't really care about the y
But we don't
coordinate,
really care about the y coordinate.
so both of those are the same.
So both of those are
So-
the same. So
For our stick
for
here,
our
problem would be enough to model 0 to 90 degrees.
Model 0 to 90 degrees.
So all the sticks are going to be, otherwise we just
All the sticks are
relabel
going
the
to be-
start.
Otherwise we just relabel the start and the end of the stick.
Okay, good. So
Okay, good.
now you can start writing some code. Let's generate and draw the result of the throws, and then model it into a NumPy array with the
coordinates here.
So we have position, which is from minus, And the other thing that you should do as you develop your program is often we also need to think about how to extend the program in the future. So thinking about some standard parameters that we can use is also often useful. Then you don't need to add them into your program later on. So one thing that is clear is that here we have the length of the stick. Call that L, and we have the distance of the track T. Those are obvious parameters. If you want to play around with the problem, then you may want to change those. Now in our case, L and T are the same, set to 1 meter, which is why I end up here with negative 0.5 to 0.5.
5.5,
But
5.5.
I probably could write that as negative T over 2.
Write that as negative T over 2 to T over 2.
And then you can even worry about the exact distances. The inclusion or the
Orders
of
the orders of the interval.
And try this for yourself now. So open up license for your up on your laptop or yeah. Or you can also run it in Google Laboratory,
Like what I'm doing there. Oh, it's cool. Actually, take some pictures of this while you're working on it. Yeah. Shorter? Okay. Yeah. Yeah. Catch more in the vision.
if you want to, you can print smaller holes.
You can print smaller holes. Okay. Okay.
But still take some pictures with your phone now, so that we have them. Because I need to write this book.
Because I need to write
So,
So minutes or so.
Not a video. I just need the.
Not a video, I just need a picture.
Yeah.
Yeah.
Every 30 minutes.
Every 30 minutes.
Or every time something interesting.
Or every time something interesting happens. Okay. It would be random, but random.
There is also non-random.
Yeah,
But
there's also non-random, but
that's if you want to apply.
that's if you want to apply for a non-high rate. So then for a whole non-high rate, you can generate random numbers.
This case doesn't matter.
In this case, it doesn't matter if you just see the. Okay. Yeah. And it will be random. You don't want to use random because if it still exists, it's
Random number.
the old random number generator, which is not with a pseudo random number generator. So at least you want to use random. Not random. That gives you a random number from 0 to from 0 to 1.
Use NumPy.
If you use NumPy, if you use NumPy.random, then you must also specify the size, like how many of those you want. So that should be n.
Where n is the number of
Where n is
rows.
the number of throws you do. How often you throw the stick. to solve more difficult ones for the midterm and the final exam.
So this is a good opportunity to practice.
Opportunity to practice.
Just like that.
Just like that, I don't think we'll get any more. MP, the land is not random. I think that's generally 90 floating point numbers from 0 to 1. Yeah, okay, that gives you and then what is X again? Only 10 points.
No, that's not what the problem.
No, that's not what the problem says, right? Like that, there should be continuous.
Generating
You're generating 10 X's and 90 T's. Like the first parameter is the size to and this gives you the size. If you put 90 there, you get 90 floating point numbers between 0 and 1, and then here between 0 and 5. And here you get 10 floating point numbers.
So here, if you want to have a look, the experiment to model it exactly as it would be. I define a function, throw sticks, which actually throws the sticks, and then it says the number of sticks that I want to throw, 5, the width of each track, and the number of tracks. And then it simply does that. So n times, we iterate through n, we generate a random number, track width multiplied by the number of tracks, and y coordinate, and I just make it square, and then theta between 0 and 2 pi, and then that's the result of my throw. So I save x, y, and theta, and append it to the stick. Now, then there's a function to draw the tracks, which also takes track width, the number of tracks, as an argument. And then, if you look at the matplotlib code here, I do keep track of the frame, and I pass in an axis object that I get from matplotlib, which is basically the canvas that matplotlib allows me to draw on. And then I call plot, which is simply to plot straight lines. For first, I draw the tracks, so they go from I multiplied by the track width to I plus 1, multiplied by the track width from I plus 1. These are the x coordinates, and these are the y coordinates of that. And then the second one is, these are the y coordinates. So it draws it as a polygon, as a filled polygon. Rectangle which requires 5 points, and then here it draws it in black. And then here I draw the actual line. Here I draw the actual stick. So for every stick, if x and y is the coordinate, then it starts at then we can sort of think of this is the center of the stick, this is the angle, theta. So at p over 2, this would be that point, right? So now I also want to draw the other half of the stick. So that's why we get plus cos theta multiplied by stick length of 2 and minus cos theta multiplied by stick length plus 2, and the negative sign and sine. And this part here you may not be familiar with, but it's a pretty cool thing to know. Whenever you draw something in matplotlib, you'll get what's called the artist, which is the actual thing that is being drawn. It will be returned. So when I call ax.plot, I basically get this line drawing that I just did. And that in itself is a line, is a list, because it may be more than one artist. So I extend the frame, and then I return the frame. So then I start a figure, create an axis object, 1, 1, 1, only one, so it's the only one. Set a title, set the label, and make sure that the aspect ratio is equal so that it looks nice. Then I generate 5 random sticks, and then I throw them here, and then here I draw them. Now, because I pass in the frame, I can collect each frame, append them to the frames, and then this I like. You can actually make an animation out of it very quickly, which is this part. And then this function here is just so that I can access this animation from my O code. So I wrote this function. You can ignore this. So let's run that. Maybe I think we can throw. And now I can show it as a HTML video. So here's our experiment. So you can see how we throw the stick. And of them. So now I have to figure out how many of those cross the line, right? And here I actually use the complete length of it. So if it crosses the line, that means it would have to go through onto a separate track, right? The start and the end point would have to be in two different tracks. So I calculate the first lane, which is the leftmost point, and the rightmost point, the x-coordinate, leftmost and the rightmost point, and then check if it's in a different track width bucket. So that gives me whether it's cross or not cross. And if you want to this, I would probably nowadays I would write it. So here, just here I just changed the code. So if the stick crosses a line, then it's painted in red. If it doesn't cross the line, it's painted in blue. So it's just going to throw a whole bunch of sticks now, and it's going to be depending on whether they cross the line. So that gives us an idea now, a better idea of how to solve that particular problem, because we can sort of visualize it, which is very nice. We can see that the track numbers don't really matter, but we also realize that the stick will cross the line if the x-coordinate is cosine of the angle multiplied by the stick length and the lane width, and 1 minus the cosine if that's bigger than the x-coordinate, if the x-coordinate is within that range. So now we have to, there's sort of a double integral that we have to solve. But that gives us because theta can be, in my representation, theta can range from 0 to 2 pi. So the probability will be 2 times the stick length divided by the lane width multiplied by pi. And then I can solve for pi using just arithmetic manipulation. So here we have the stick length, and that means that this particular test here, throwing these sticks without knowing anything about the width of the track or the angle that they come down at, actually allow us to estimate the value of pi, which is surprising to most people. And in fact, the probability that you will get if the stick length is the same as the track length is actually 2 over pi. So here I can count the number of times that we hit the probability that we crossed the line in the sticks that we threw. So if I have, so now I start with how many X's? 500. And so I'm going to throw 500 sticks. I'm not going to plot all of them. Then calculate that probability. And if I get it, then the estimate of pi would be 2 times the stick length divided by the track width divided by pi. If stick length and track width are the same, if they're both 1 meter, then that would be 2 divided by pi. And then this is my estimate, and here we can see the result. So here, this is how many sticks I throw. then here's the result. You can see that uh, 3.14, the actual value of pi is this black line here, and you can see that even after say after 10,000, the value converges pretty nicely to the correct value of pi. Which certainly came as a surprise to me when I heard for the first time about this problem, because throwing sticks on the actually the Count Buffoon he used toothpicks on a tile floor, but same idea. Um, it's pretty surprising that that relates to pi, right? And it's a nice exercise to sort of showcase some of the capabilities of Python, NumPy, and Matplotlib, which are indeed quite powerful libraries. Um, if you do any kind of machine learning, deep learning, AI work nowadays, then a lot of the code is written in Python using NumPy, Matplotlib, and then also PyTorch as the deep learning library. So this is a very common workflow nowadays, kind of visualization for AI systems. So I suggest you go through that. You can also modify the data structure. Like I said, we could have canonicized the representation by limiting it to be between minus t over 2 to t over 2 instead of actually having the number of different tracks painted. But this kind of looks cool too, so I like that part too. Drawing the animation with Python. So any kind of visualizations like that, it certainly helps me a lot trying to work out the problems to often to implement a small simulation at least, so that I understand the problem better. And this can be done quite easily with Python. Then let's see, for our course, You want to withdraw? Okay. Yeah. No problem. Okay, good. So let's talk some more about current AI trends and language models and large language models and small language models and the current state of affairs. So for the next 30 minutes, you can do some research on your own, so you can use the computer. And what we would like to figure out is one of my particular research interests, apart from intelligent robotics, is also this idea of applying sort of more efficient machine learning, more efficient AI at the moment, being able to run small language models on your laptop, I think will have great applications in robotics and intelligent systems and physical AI, which is what they call them now. The one of them that is obvious is if you run it on your own local computer, then you don't need to worry so much about having your data stolen or copied to some. So there's a very good reason just for privacy and security um, that would make it desirable to be able to run your own language model on your own hardware. And that seems to be becoming more and more important nowadays, given the current political climate. So, in order to make that um, possible, though, we need to have a look at how much compute is actually required for the new models and how much computing power is actually available um, for executing these large language models. So, how many? Some of you may have heard of maybe familiar with Moore's law, right? Which states that quadruple, but close enough. Yeah. It'll be 4 times. It'll double every 1.4 years, whatever the law is. I think they doubles every 2. Okay. When I was growing up, it was quadruple. But okay, we'll go with double. The point is that it is growing exponentially, which is why we have had these great. Actually, this exponential growth was observed by Moore in the mid-60s already, and then for a long time it has sort of held true. And then every decade or so there's there's sort of paper or articles that say, oh, now we come to the end of Moore's law, and it's finished now. But then something happens, and then it seems to be progressing even up to today. Whereas the first prognosis that Moore's law was not holding up anymore, we're sort of in the 90s. That's because the actual number of transistors sort of kept increasing, but then that didn't really lead to more faster CPUs for a while. The reason was that the bottleneck really was not so much the processor, but the memory count, sort of the memory bottleneck to the RAM to be able to access all that data fast enough. But then caches became bigger and bigger, so a lot of that latency, a lot of that bottleneck could be sort of averaged out over time using caching. And also, nowadays, you don't have, other improvements were in processor design. In the old days, you had
So here, if you want to have a look, the experiment to model it exactly as it would be. I define a function, throw sticks, which actually throws the sticks, and then it says the number of sticks that I want to throw, 5, the width of each track.
In the old days, processor performance was defined by 3 parameters that sort of work together. Of course, your processor had to execute instructions. Right? To execute the instructions, one of the critical parameters would be the clock frequency. So if you had a processor that would run at 1 gigahertz, and you have another processor identical that runs at 2 gigahertz, in microcontrollers and the very early processor designs, you would expect it to run about twice as fast. right? Assuming that your workload was actually CPU buffed. And assuming that your memory also was twice as fast, access to the memory was twice as fast, or access to the cache. But then it wasn't just the frequency, but also the CPI that was important because the clock cycles per instruction were CPI. Became important because you had instructions like divide or multiply, more complex instructions on the newer processors. But with they would not execute in one clock cycle. It would take like 16 or 32 clock cycles before you could get the result of a division or something like that. So you had to take all of these three factors into consideration when you wanted to evaluate or estimate how fast your processor or computer system was able to process a particular workload. Now, there were a lot of games that you could play with this. You may have heard of this versus RISC CPUs. That's an old classification of CPUs. RISC stands for complex instruction set. Computer RISC is reduced instruction set. And so, for a while, there was a big gap or a big fight between what kind of processing design would be better. And this is kind of the Intel CPUs, your i7, i5, so forth. RISC was actually started with ARM and MIPS kind of processors. And they really played up on the various factors here. Because for a long time, the only parameter that people thought about was the frequency. So people would say 8 megahertz, 16 megahertz CPU, for example. And then you had all of a sudden RISC machines that had 32 megahertz, 64 megahertz, 1 gigahertz. So their frequency was very, very high. But they achieved that by fiddling, and their CPI was very good too, because their claim was that they could execute every instruction in one clock cycle. So that should have made them blazingly fast compared to the Intel kind of processors that were running at a slower clock frequency and had higher CPIs, 2 or 3 instead of just 1. But then in practice, for some workloads that worked well, they were very fast. In other workloads, they were not so fast. So on average, it kind of averaged out, and they were both the same. And here, the big difference was what is considered an instruction. So for a CISC processor, divide would be one instruction. Divide to 32-bit register was one instruction on a CISC processor. To do the same thing, the RISC processor would have to call that instruction in a loop, a partial divide instruction in a loop 32 times. So then it meant it also couldn't divide numbers faster than you would expect. So for a long time, these were the three parameters that were crucial for determining the performance of your processors in early 2000s, late 1990s. big change. And the reason why we're still talking about Moore's Law and the fact that it kind of has been progressing like this for so long is that nowadays we need to worry a lot more about parallelism. Because your desktop CPU nowadays doesn't have a single core anymore, but there's four core, 8 cores. Mobile phone. I was blown away when. God, which phone that was? Maybe. 2010, 2012. I bought a phone. Asus Zenfone 2. And I was honestly blown away when they told me that that phone had 4 cores in it. That seemed to me insane that you need 4 cores, 4 processors, CPU cores on your mobile phone to make phone calls. I found that, and nowadays they have even more. So a lot of it is parallelism, and now of course for AI workloads in particular, this parallelism is sort of not the general type of parallelism that we have in CPU cores with general processors, but the specialized cores that were originally developed for 3D graphics in order to be able to show nice games and 3D visualizations. So the kind of linear algebra parallelism, which is in fact the compute power that GPU. And nowadays the most complex, the chip with the largest number of transistors in your computer is not your CPU anymore. But usually it's like trillions of. Check how many billions of parameters. There you go. So this is 1 billion processors. But that's 2005 up to 2005. Recent one. Oh, this. 63 million. $50 billion. But these are all parallel
But these are all parallel architectures.
I wanted to show the animation.
And I wanted to show the animation.
So the Moore's law has been chugging along up to our times for sure. And now we're at 50 billion transistors for the most complex CPUs. Billion, 100 billion. You can sort of see if you plot it on a log scale, it turns out to be basically a straight line. But the y-axis here is logarithmic: 10,000, 100,000, 1 billion, 10 billion, 100 million, 1 billion, 10 billion, 100 billion, and then here this would be 1 trillion. But what about compute? So you would think that our I guess the other part of Moore's law that is kind of relevant there is that the transistor counts keep going up, but the prices stay relatively the same. If the i7 CPU would cost also twice as much every 2 years, nobody would be owning a computer anymore, right? Because if you had a computer that, if you look at the same curve, if you had a computer that cost $10,000, if it follows the same curve, if you had a computer that cost $1,000 in 1970, it would cost $10 billion now. So nobody would be owning personal computers anymore. So the fact is that the costs don't go up at the same rate. So modern CPU make extensive use of parallelism, so they all have multiple cores. They use hyperthreading. And are also superscalar. So what's a superscalar architecture? Superscalar means that here, when I talked about the clock cycles per instruction, different types of instructions have different clock cycles depending on how complex they are. How many clock cycles per instruction nowadays for CPU? For Intel CPU? One? One is sort of the maximum. In fact, superscalar means that the CPU is executing more than one instruction per clock cycle. So modern Intel CPU executes about 6 of them, if it can. But to be able to get that kind of speed up, you do need to be quite concerned about, like if you wanted to optimize code of on a microcontroller, then what would be, how would you try and make the code run faster? If it's nowadays on a microcontroller or 30 years ago. No, you can't. You are given that hardware, you're trying to make your code run faster. Pardon? Dividing the workload, how? There was a lot of, maybe more than nowadays, where our hardware is really fast enough to do most workloads in a blink of an eye, so most people don't care that much about performance anymore. Except when they're running large language models, because that's a huge workload. If you're just storing data in a spreadsheet, you'll never notice any slowdown. But there's kind of 3 things that you can do. The two that you can attack, right? Here's the GPI. That one is fixed. The frequency is fixed if you don't change the hardware. So the only thing you can do is change the instructions that you need to execute in order to run your code. Now, optimization techniques that were used at that time, or even nowadays, a microcontroller that can be very useful and can be very successful. Like we actually implemented a full 10 frames per second local vision system on a 68,000 CPU by doing all kinds of tricks like that. So one of them is a loop. If you implement a loop, you want to count through an array to sum it up or something like that. Right? Then you would have something like for divided in C. If you write it in C, I is equal to 0, I is equal to 0, I less than or equal to 1024, 1024, I plus plus. Sum is equal to array I. Right? That would sum up through the array as long as your array is initialized to 0. Now, one way to make that faster, or when this translates into assembly language, then executed on the CPU, this will be kind of like I is equal to 0, so that will be store R0, 0, for example. Then you want to load the array. So load R2, R1, R1 into R2, R1 into R2, add R3, R2, increment R0, less than R0, R4, where R4 is 1024, branch less than to label 1, L1. This is kind of what the assembly language looks like. That's what you would get. And you can kind of see there's instructions that have to deal with the actual add that we're doing, the actual work that we're doing, right here. But that's only those two. And these instructions, these two instructions here, they actually only take care of the loop, right? They only count up to 1024 and then branch on less than. So for every loop iteration we execute 4 instructions, but only 2 are actually relevant to what we want to do, what we need to do. So I can rewrite this. Actually, here I need to increment. R1. So there are 3 instructions that don't do anything to that actually increment. So one way that is very common is to unroll a loop, which is what it's called. So here we execute get R0 to 0, then R0 to load, then R2 load R1, add R2 into R3, then we load R2 1 4 if it's a 32-bit or otherwise just integer, or otherwise just 1. So we have a displacement to our 1 register.
to our R1 register,
we load
add,
R2,
then we load R2, R1,
add,
R2,
and
then
we
we
do
add, and then we do 1 add, 2 add, 3 add, 4 add.
So basically, I take that loop and I unroll it. Then I need to add
unroll it. Then I need to add
4 to
4 to
our
which one? R is it? R.
then I increment.
Then I increment.
But now I don't need to branch on pen 24, but I need to branch
on pen 24, but
4
I need to branch
divided
on
by
pen
4.
24.
Every loop I now count
Because
4. I do 4 additions.
count
Right? I take 4 elements and add them together.
Right? I take 4 elements.
So that's called loop unrolling.
Loop unrolling.
But today, this happens all the time in your code, except that the C compiler, the Python compilers, they're all smart enough to do this automatically for you. But that was one of the ways in which we were trying to optimize our code. Other optimizations were things like reducing the power of the operation, changing the instructions. So for example, there were a whole bunch of arguments about this, but if you divide something integer by 200 by 64, so you want to calculate R3 divided by 64, you can use the divide instruction for integers, and it'll give you the result. But often divide was the general division routine, so it has to go through, and for 32-bit operands, it basically needs to execute a loop 32 times. You can do the same thing by doing logical shift right on R3 because 2 to the 6 is 64, right? If I shift the result 6 times to the right, then I also end up with a division by 64. So powers of 2, the logical shift right would be a lot faster than a divide operation. On a microcontroller. This is all still relevant for microcontrollers, but not really for desktop CPUs anymore. So here you have the power reduction. That's also done nowadays by your C compiler most of the time. Unless it's very specific kind of division, your C compiler would be able to. And the whole point of optimization at that time was to try and reduce the number of instructions that you had to execute. So there were all kinds of clever ideas for how to do that by unrolling branches. You could often get rid of branch equal, not equal kind of instruction by changing the operand, overriding the operand. On a superscalar CPU, that really doesn't make a lot of sense anymore nowadays, because all of these instructions, like I said, for the Intel i7, it can execute up to 6 instructions in parallel. But it can only do that if you actually have no data dependency. Right? So if you execute this code here,
execute this code,
we have this simple loop here, and you want to run it,
we have this simple
then
here.
there's a very strong data dependency, which means that you really cannot execute this very fast, because before I can calculate this value of sum, I need to know the previous value of the sum.
I need to know the previous value of the sum.
So every time through the loop, the addition must finish before I can do the next addition. So this data dependency means that your i7 CPU basically can only execute like one or two instructions, because otherwise it's going to hit. It needs the value of sum, but it doesn't know what that value is at this point. So it has to wait. It has to stall. So then some additional increment or branch instructions here are basically just going to be filling the rest of your CPU pipeline. So there's really no penalty. Extremely difficult to write code that has all that can execute 6 instructions in parallel consistently. However, these data dependencies are an issue. If you really need to do that nowadays, you can use the i7 SIMD instruction to do this in a couple of clock cycles without any data dependencies, and that's what actually NumPy uses to calculate sum. If you call sum, it uses very highly optimized routines in order to actually calculate that. If you want to do that, a little bit faster, but not quite so optimized, so that you need to know all the details of the CPU, then it would probably be about twice as fast if you rewrite that loop as sum 1 is plus equal array I plus array,
and sum 2 plus equal array
plus 1, and then sum
is equal to sum 1.
And why is that a lot faster? Or why can that be a lot faster? Correct, yes. Here I got rid of the data dependency, at least for a little while. Because this one here depends on the value of sum 1, but this one only depends on the value of sum 2. So those two can actually be executed in parallel in your superscalar CPU, even if you don't have any special vector instructions. So nowadays, this is the kind of thing that's harder to figure out for your SQL file. So you don't really need to worry that much about loop unrolling or anything like that. But you need to think carefully about the data dependency. And the other thing that you need to care about very much, that is also crucially important, much more important than trying to reduce the power of your instructions, is that if you have an image, 1024 by 1024, you can do some kind of image processing on the image, you want to run a convolution or an edge detection or something like that.
Now,
you want to go through the image this way, row by row, or do you want to go through the image column by column?
Column by column.
Row by row, and why?
Row by row, and why?
Okay, the data in arrays is organized this way,
data in arrays
right?
is organized.
But why does that make a difference?
But why does that make a difference?
Yeah, the axis changes, but what changes if I change the axis?
But what changes if I change the axis?
This will, if you go column by column,
This will, if you
if you go the red route,
if you
like row by row, then your code will be a lot slower.
Your code will be a lot slower.
And the reason for that is because of caching. If you access this pixel here, then your CPU, if you asked it for one integer or 1 byte, your memory controller is not going to load 1 byte into the CPU. That would be way too much work for the little game. So on your CPU you have your caches. And nowadays there's 3 levels, L1, L2, L3. Which are much faster than main memory access. But they're limited in size because they are more expensive. They have been growing up in size. Nowadays,
I would expect definitely
16 megabytes, I'm sure, is already a low.
16 megabytes, I'm sure, is already a low CPU nowadays.
So if you read this byte here in your computer vision program, your processor is going to take an 8 kilobyte block, roughly about that size, into the L1 cache at least. And if you then read the next byte, this byte here will be already in the L1 cache. So you have a whole bunch of bytes that are in the L1 cache already. If you go down this way, then this will be 1024, so this will be already be 3 kilobytes away. So that means this byte here will be at the end of the cache, or it will have to request another memory access. And then, as you use up your 1024 here, you run out of L1 cache, so the CPU will have to throw away some of the data, which means it'll flush your cache, and by the time you read this next byte, you have to read in all the data from it. So your latency then will be completely determined by the dynamic RAM to CPU bottleneck. And that can be hundreds of instructions where your CPU just sits idle waiting for the memory controller to send you the data. So nowadays, optimization is not so much anymore on the instruction level. A lot of this can already be done by optimizing C compiler or similar compiler. It's much more on laying out the data in your memory. That can have huge performance implications. So, for example, if you do a convolution, like in Photoshop, you want to do some operation on a certain set of pixels, or in a computer vision application, then they actually check what kind of CPU you're running to figure out the size of your L1 cache, so 64 megabytes. Then they're going to split that picture up into 64 megabytes blocks, and they're going to send you that block to your CPU, and then if you do all kinds of convolution operations, flood fills, that whole bitmap is going to be in the cache, and it's going to run very, very quickly. And similarly for NumPy, they're trying to do slices in NumPy. They do the same thing, trying to get the data into your cache. So let's say this was also a big optimization thing that people always cared about, which was removing jumps. Nowadays, if you have a jump, unconditional jump, go from here to there in your instruction stream, it won't slow down your CPU, guaranteed, or almost guaranteed, because extremely unlikely that you have all 6 superscalar slots filled. So there is always a way that branches, of course, are a big problem in optimization, because for a branch, that is always data dependent. You don't know whether the branch is taken or not until both of the operands can be evaluated. That's why for superscalar architectures, they're trying to optimize branches by using the branch predict cache. So branches backwards are assumed to be taken, branches forwards are assumed not to be taken, and then the CPU simply will assume that the branch is taken or not taken, and it'll execute the next couple of instructions. Once the result is available, then it will say, if it predicted correctly, it'll just continue. It will have saved some time. If it's not correct, then it will have to undo all the operations that it did, and then start processing from the branch point again, which can be a lot of work in itself, but we have enough transistors to do that, and somebody figured out the control logic in order to be able to control that, and so that's what the CPUs do nowadays. So things seem to be um, going well for us, right? We have very powerful CPUs, exponential growth for 30 years, since the 60s, so 70 years. Now let's have a look at the AI system and the large language models and have a look at the growth of those. The whole thing started in early 2000, not about 2018, which was GPT. But they weren't so general. But they do mention the vec to word to vec algorithms and the BART systems. So starting in early 2000. I was hoping. So here's a chart from Wikipedia which shows just from 2017 up to 2025 the amount of computation that is required in order to train the various language models. And so in 2027, the plot starts at 10 to the 23. Right? So this is also a logarithmic plot here. So 10 to the 23. So what is that? That is billions is 10 to the 9. Quintillion, I don't even know what that is. The one with 23 zeros. There's no 106 billion. 6 billion. A 6 billion is 10 to the 21. So here we have 106 billion, 1,006 billions, and 10,006 billions. The various language models. GPT-4 is labeled here, Gemini 1, and the time of its publication. You can sort of see that this curve is also a straight line going through the also a straight line going through the logarithmic plot. So it also grows exponentially, and this would be so if we look at the growth, then let's say from 2021 to 2023, we get from the top model in 2021 would be here. In this time frame, the next one is the top model 2023 to 2025 is up there. So in those between those 2 years, basically the compute grew by about 100 times, not just 2 times. So that means that even though our CPUs are improving, even if Moore's law holds true, the size of these AI models is just getting astronomically large. That's why they're building larger and larger data centers everywhere. So the size and the the amount of work that it takes to train these models grows up faster than what Moore's law even can provide. And Moore's law in itself if you think about it, is a phenomenal speed up. Like this exponential growth curve for such a long time is unheard of in human development, human technological development. If you don't think so, then just think about let me just add this here. According to Moore's law, the number of transistors doubles every 2 years. So we just say, okay, that means that roughly the speed doubles every 2 years. Right? And how do I get the cost in? We think about the cost for CPUs, right? Um, comparable, if you bought a PC in the mid 1990s, it would have cost you about the same as nowadays. So let's say about $2,000, right? Give you $3,000 in 2000. 1966. Let's take 1966. And nowadays, we bought, for this course, we bought some Pico 2. How much did we pay, David? Yeah. 200 NTD, so that's about $6, right? $6. So now you are from Spain, right? Barcelona. How about an airplane ticket from Taipei to Barcelona? €1,000, 1,500 USD. We just go approximately here. It would have cost the same in 1996, approximately, because the airplane fares haven't changed that much. And how long does the trip take? 16 hours. Okay. So if airplane travel would have followed the same curve as Moore's law, then how long should your trip, if airplanes had speeded up as much as CPUs, then how long would the trip take from Barcelona to Taipei nowadays? If it was uh, 16 hours in 1966. Time would have been 16 hours, right? Which is 16 hours. Now it doubles every 2 years. So 2 years later, 1968, it would have been 8 hours, right? Then 1970 would have been 4 hours. So it would be 2 divided by 2026 minus 1966, right? Divided by 2. So that would be 1.4 times 10 to the minus 8 hours, right? So it would be this many seconds. So it would be this many milliseconds. This many 53 microseconds should be what your trip from Barcelona to here would take if airplane would have followed we all would have really enjoyed that, I think. You wish, right? And the cost would be so here we need to figure out what the here we need to figure out what the exponent is of the decrease, right? So that would be be divided by b, or the cost ratio to the power of 40, 60, that's 60 years, right? 1966 to 2026 is 60 years, so divided by 2 is 30. 30, so that means the logarithm of cost 2026 is equal to the logarithm of cost 1966 divided by CR to the power of 30. Now, the logarithm of x times y is equal to, remember, plus, right? It reduces the power. So multiply becomes plus, division becomes minus, correct? So we have this. So this should be log of cost 1966 minus the log of CR to the power of 30, right? Which becomes 30 times the log of CR, right? And now I just need to turn that into Python. Oh, actually, I need to solve it. So now I want to solve for the log of CR, which will be divided by 30. And then we need to calculate the exponent. That should be correct. That'd be 81 cents for the ticket. People do a lot more travel at these prices. But yes, so obviously air travel, optimizing air travel is much harder than optimizing transistor counts. But this kind of growth for CPUs even is incredibly large, huge. Incomprehensible what kind of computing technology they used in order to fly people to the moon in 1969, right? But LLMs, the amount of training CPU usage that they use that are necessary in order to train the next generation of large language models far outpaces that of Moore's law. So we have to come up with more efficient training regimens, better algorithms, highly specialized hardware maybe for running language models, except that GPUs are kind of like really well suited to that particular task. So I don't see there being much that can be done. But in this course, we'll be focusing on being able to run smaller language models, less than 8 billion parameters in size, which we can actually run on a local machine, both for security reasons and lots of other reasons for running it. But one is that eventually we will run out of the CPU power that is available for these large language models. So we'll be ending up with smaller models. But I do believe that even for these small models, there's a lot of interesting things that we can do with them, especially in robotics, if we can sort of extract the physical underlying intuition that the model develops. And this is kind of what we want to do with the course here. Both related to robotics as far as perception is concerned, as well as manipulation and control. So very interesting times right now. Okay, good. Then that's it.